with us. And when I was asked to introduce him, I realized that my memory is totally full of holes and everything. So we do unusual thing that Bhiksha will introduce himself. So I would like to ask Professor Bhiksha to introduce himself and tell us where he came from and what his life was until this point and what nobody sees in the future. So.
Bhiksha, begin by saying, long ago I used to be called Mr. Sphinx.
Mr. Sphinx is...
Oh yes, there are several of us who are called Sphinx people. So good afternoon all, it's already past 12. And thank you for inviting me to give this talk. I'm Bhiksha Raj. I'm an associate professor at Carnegie Mellon University. I work on a variety of topics related to speech and audio processing, machine learning, and lately a little bit on privacy. I've been working on speech and related areas for a very long time. So in fact, the very first time I met Enoch was in June of 1994 at a Rutgers workshop. So I've been around, I'm even older than I look. Anyway, so I've gotten to the stage in life where when I claim that I'm working on something and I make presentations, what I really mean is that I have students who are working on something and I'm talking about things I have no idea of because they know everything. So for this particular talk, the main culprits are Manas Pathak, who graduated last year, and José Portelo, a student at INESC in Portugal, who I am co-supervising with my co-conspirator Isabel Francoso. So, in the process of mentioning that I'm old, I must kind of mention that I belong to the generation who discovered the internet. One day we woke up and suddenly you logged onto the computer and there were all these beautiful bulletin boards. Like you could go on comp.os, you could go on sci.math or soft or something or the other, and there were people on the other side of the planet who were discussing stuff, and you could post questions, you could make comments, they would reply to you. And we did this freely. I mean, we didn't pause to think for a moment that when we posted something there, we weren't merely doing it for the people who are reading it right then. That stuff was going to be there forever. So now, fortunately, I was a geek, so everything I posted was on sci.math and comp.os. But now, 20 years later, when I go on Google and type my own name, all those posts come back. And I just thank my stars that I didn't embarrass myself. I could have been on all.binaries.pictures, right? I could have been posting stuff, and that stuff would have been there to embarrass me in front of my students, my relatives, my children, and it's something I wasn't thinking of. 20 years have passed, more than 20, and people are still doing the same thing. So, but except now, voice processing is the latest set of bulletin boards. All of us are using Siri. We use voice processing systems all the time. And we don't stop or pause to think that everything you say is being recorded by someone somewhere, and that person's or that organization is going to have it forever. Now, is this a matter of concern? So here are some organizations or some newspapers who thought it was. And I'm just sort of trying to weave it into my story, but I must be honest, this is just a shameless plug to say that, hey, some of the stuff we worked on has appeared in various newspapers. So MIT Tech Review, and I'm particularly tickled at this having appeared in The Economist, and I'm not so sure about Fox News. Anyway, so the point is, all of them voiced the same concern that we did, namely that people are just sharing their voice, and we don't really worry about what's happening with it. Now, you might notice, I don't think you can actually read it, that all of these articles are from 2012, and there's a reason for that. Why all of this hullabaloo in 2012? It started with an article in Tech Review by David Talbot, this had nothing to do with us, where he observed that Siri was becoming very popular. And every time people used something like Siri, they were handing out their voice to Apple. So his actual quote was that people using Apple's digital assistant share a distinct concern, blah, blah, blah. They go to Apple, the stuff remains stored there. And what is the problem with that? The voice recording, unlike data produced by smartphones and other computers, other data, is an actual biometric identifier. It can be used in a court of law, if you think about it. And now, if some hack, Apple, a malicious organization, anybody got hold of it, the stuff they can do with it is, fairly unlimited. And it isn't just Apple who's storing your data. What are the concerns? Now, CD, or a hacker who breaks into CD, I'm using CD as an example, but really we're speaking of any odd voice processing, any company which wants your voice. They could edit your voice recordings, and suddenly you find yourself on the web saying things you never really said. Or they could use your voice recordings to find out about your gender, your identity, your state of health, your emotional well-being, your state of emotion, everything. They can create models for you, and they can use these to track your behavior. They can spy on you to find out where you've been, what you've been posting, even if you think you're anonymous. And this isn't specific to Siri. In fact, it's already a problem. So here are a couple of, Gerald Friedland over at ICSI has been working on identifying these problems. User verification, matching the uploaders of videos across accounts. Here's another paper, linking personas based on modeling of audio tracks of random Flickr videos. These are people who think they're anonymous because they haven't assigned names or given out their names when they upload these recordings. Guess what? They are not anonymous. And and it's not just voice, just as an aside, a couple of years ago, Alessandro Acquisti in CMU had a scary paper. Now, it's been known for a while that if I know your place of birth and your date of birth, I can pretty much find out your social security number. Now, what Alessandro did was to show that if you had pictures up on Facebook, they could use a face detection algorithm to find you. And then they could use that, and then they could use your Facebook account to get the other details, from which they could get your social security number. So you might actually be walking through some, and he ran an experiment where he showed that this was indeed possible. So you might be in some unknown market in Egypt, Cairo, thinking you're safe. Some shopkeeper takes a photograph of your face. By the time you go to your hotel, your bank account is cleared. This can happen. And so anyway, now these are all malicious, possible malicious acts. But there are also other cases where people are actually concerned about the privacy of voice, and this gets in the way. So for example, doctors, lawyers, and government agencies have large quantities of voice recordings which they would like to have transcribed, but they can't just ship it out to Google Voice because of HIPAA laws and other kinds of laws which protect the protect the information that is in those recordings. Or speech data warehouses have large quantities of speech data, they'd like to get it mined. They can't just hand it out because people read out their credit card numbers, their social security numbers. You can't let anybody know this. And here's another one, just making more of a case, and this everybody's favorite president, George Bush. Of course, this kind of news has become increasingly popular, but I still have this old clip because it was the first time something of this kind really appeared and made a splash. Despite pledges by President Bush and American intelligence officials to the contrary, hundreds of US citizens overseas have been eavesdropped on by the NSA. So what is the concern here? Now, the NSA has a reason for doing this. It's not like they're getting their jollies out of listening to people. They are worried that the caller is a miscreant, or he may be planning, or he or she may be planning some bad activity. But in order to find out if this is indeed true, they have to listen to everything. Now, NSA is really not interested in listening to some poor person calling his wife and discussing dinner. They are looking for a specific person, a specific voice, a specific phrase, but they can't just find it without listening to everything. So all of these are problems of the need for what we will call privacy-preserving voice processing. Now, the majority of the world's communication over the eons has been by voice. And over the eons, everybody has realized that voice is a private form of communication. We don't like to be eavesdropped on. In many places, you can video a person in public, but you can't record their voice. Yet, if you think of the best technology we have to date on how you can hide what you're saying from others, we've only developed whispering, and we've developed counter-espionage technologies for those too. So, solutions, we really don't have a solution. Now, amongst the speech processing community, there is a fallacy that by somehow extracting features from our signals, converting them to Hepstra or whatever else we might like to convert them to, we have somehow erased the information in the signals and so we are safe. The answer is no, that's not the case. If I have features derived from your signal, I have everything about you. I can recognize those, I can use those to find your gender and all the other good stuff that I mentioned. I can even use it to synthesize your voice. So clearly, this is a protecting audio needs more than simple parameterization. Now here is another instance of an illusion of providing privacy. This is
the contest. What do we call? Sean?
from a movie called Ransom.
Oh, Jesus.
I want $2 million.
So, that goes on for a bit. Now, this was the mandatory little movie clip to keep you people engaged for a while. Anyway, so the point is, the bad guy is trying to hide his voice, and he thinks that by simply shifting the pitch, he solved the problem. Now, again, that's a fallacy. You call your parents, you call your mom, you have a cold, your pitch has changed. She still recognizes you because she recognizes you not on the pitch of your voice, but on how you speak. So obviously this isn't hiding any information. So what we are really looking for is mechanisms. Now, there is a great deal of research on trying to erase the information in voice recordings, trying to erase the person's identity, trying to erase the information about what they're saying. And it's an interesting problem. I personally believe it's the wrong way to go because it's really not going to be feasible. So we sort of looked at the alternate possibility. We want users to be able to use voice processing systems without risking loss of privacy. So really we have an issue of computation without trust. And the trust, what you trust the system to do, what you believe the system is capable of, depends on the setting. So there are very many tasks under which the same issues apply, speech recognition tasks, biometrics. And specifically today's talk is all about biometrics and speaker verification, yes.
I'm sorry, why can't, this may be obvious question, but why can't you just transcribe from speech to text, and then using a generic synthesizer to synthesize part, a male or female or whatever voice, from the text,
Yes, and again, it all depends on what you're trying to hide, right? So here we're speaking of a specific server client setting. If I want to send my voice over to Google for transcription, for instance, then the text is the information I'm trying to hide. If I'm trying to use this for biometric identification, converting it to somebody else's voice doesn't help me at all. I really want my voice, right?
Yes.
So now, what are the issues in biometric identification? Again, if I'm Apple, let's say you're authenticating yourself to Apple by voice. Afterwards, I have your recordings, I have your models, I can use this to spy on you. I can track all the YouTube recordings where you spoke. I can find out every time you enter a store and speak to a sales agent because I know what your voice sounds like, and that's what we're trying to hide. Now, so let's concentrate on biometric authentication because this turns out to be the easiest of the various problems I mentioned in this context. Many services need authentication, and this is conventionally performed using passwords. Passwords are something that you know. The alternate mechanism is to use biometrics, which is based on something you possess and cannot lose. And so you don't need to remember stuff, and of course these two can be combined. And in situations where you have little keyboards and such like, the most obvious biometric is your voice because it's very easy to record voice. So this is what we're going to work on, but we want to make this secure. Now the basics of biometric voice authentication, a person claims to be somebody, they say I'm John Doe, and the system must verify that they are indeed John Doe based on something that they know about the person. And so there's an enrollment phase where the speaker enrolls with the system by providing a bunch of recordings from which the system creates a model for the user, and then the user provides news. Then at some point someone claims to be this person and provides a new sample, and the system compares the sample to the model to authenticate. Now, there are very many versions of this, text dependent where a person speaks a specific phrase, or text independent where the person can say anything at all. We are going to assume text independent operation, but this can be extended, yes.
I would have guessed that most of the systems do challenge response. So that'd give you some novel phrase and you should repeat it back.
Yes.
I mean, that's vulnerable to synthesis, obviously. But
So over here I'm assuming text independent operation. Pretty much everything that we're talking of can be adapted to the challenge response scenario too. All we are trying to do is to protect the voice. And what they are saying is not necessarily something we want to hide in this scenario. So just a quick note, when I speak of a speech signal, I'm not speaking of the samples themselves. I'm speaking of a sample of feature, a sequence of feature vectors derived from the signal. And that's all the slide is really trying to say. So now the basics of how speaker authentic verification is done, very quickly in a few slides. We are all familiar with the notion of Gaussian mixture models. It's a convex combination of Gaussians. And so when we want to perform speaker verification, the most basic approach is to train a Gaussian mixture model distribution from the voices of many, many, many speakers. This represents the universe, everybody except your target speaker. What we'll call the universal background model, and which I represented using the symbol lambda u. And then when the user tries to enroll, the user's recordings are used to adapt this background model to the speaker's voice. So you get a new model lambda s, and typically if you don't, we won't have too much enrollment data, so you won't adapt all of the parameters of the model, just a few, like the means. Anyway, so then when a new recording comes in, the probability of this recording is computed using the background model and also using the speaker's own model. And if the probability computed using the speaker's model exceeds that from the background model by a certain amount, you verify that the person is who they claim to be. The issue here is that in the process, the system needs two things. It needs this X, which is the speaker's voice, and it has the lambda S, which is the model for the speaker. And of course, this means that it can use the speaker's voice to do all sorts of evil things, like we mentioned, and it can use the model lambda S to track the speaker, which is something that we also don't want. So we really want to be able to perform this entire operation without letting the system see the X or the lambda S. And yet, we wanted to be able to authenticate the person. Now, this kind of seems impossible. And as it turns out, it really is not. It's a very simple problem. What we really mean to say is that we don't want the system to be able to listen to a recognizable version of the speaker's voice or have a comprehensible version, something that it can understand of the speaker's model. So the system may have encrypted models for the speaker, something inside a locked box which it cannot unlock. The speaker can encrypt the voice and send it to the system. So put it in a sealed envelope and send it to the system, just so long as the system can't unseal the envelope. And now the problem is simply that of determining if what is inside the sealed envelope matches what's inside the locked box without opening either. And this can be done using secure multi-party computation. Now, again, all of the of what follows, I'm assuming that the user has a computation-capable device, like a smartphone, and all communications between the user and the system are done with the smartphone, and that the smartphone can be trusted. We have to make some assumptions. So, secure multi-party computation is a fairly simple concept. We have a group of people who wish to compute some joint function of all their inputs, but they don't want to reveal their inputs to one another. Now, in the ideal situation, you'd have a trusted third party sitting somewhere in the middle. Everybody simply sends their data to this third party who performs the computation and returns the answer. Nobody finds out anything, everybody is happy. In practice, you're not going to have the trusted third party. So now we devise a mechanism where everybody talks to everybody, but using specified protocols. And in so doing, they're able to achieve what they actually set out to do in the first place without actually using this trusted third party. And here's a simple example. A group of people want to find out their average salary. Now, nobody wants to reveal their own salary. So, and yet they want to find out the average. And there's a very trivial solution to this. I could start off, for instance, by adding a random number to my salary and handing it to the next person. Now, because there's a random number added, they don't know my salary. They can add their own, hand it off to the next person, who adds their own, and so on. And it goes all around the room, and when it comes back to me, I'm going to have the sum of everybody's salaries plus the random number, which I can subtract. We've got our answer, nobody found anything. So we have protocols of this kind, which can actually be used. We make some assumptions. Specifically, we are assuming that nobody lies, that they're allowed to analyze everything that they got, but they won't lie about what their own salary is. Because if they do, then the entire protocol breaks down. There are ways of going around this, but this is the assumption we'll make for now. So, using this sort of protocol, here's the basic mechanism. We have a user Alice, we have a system Bob. Alice has input X, Bob has Y. We want to compute a function f of xy without exposing their data to one another. And the kinds of solutions the protocols will give you are given here. In one variant, Alice and Bob will both get seemingly random numbers, but the sum of the two random numbers is the actual result. Or Bob could get an encrypted version of the result, which only Alice can decrypt. Or Alice can get the actual result. Well, so we won't get into the details of this, but all of this can be achieved without exposing data. And we can define these for various operations, like inner products of vectors, finding the maximum component of the sums of vectors, or the index of the maximum component of the sums of vectors, and so on. So, just assuming that all of this is possible, in the conventional computation, when Alice and Bob want to compute something jointly, Alice sends her data to Bob, and Bob uses his data and Alice's data. He passes both into a monolithic algorithm, which gives him a result which he can ship back to Alice. In the SMC scenario, Alice and Bob are going to compute everything collaboratively, and the output of each step is going to be passed on to the next step, and the problem is all about how you decompose things into steps. So without going into further detail, I'll just claim that this kind of computation can be used to achieve our results. So for example, in the enrollment phase, Bob can compute the UBM, and once he has Bob has the UBM in clear text, but once he has the enrollment data from Alice, he can actually compute encrypted models for Alice from her enrollment data without actually seeing Alice's data. And during the authentication phase, he can get encrypted data from Alice and decide if this is indeed Alice by comparing it to Alice's encrypted models and get the result that is desired. So it works, and it's correct. It's mathematically provably correct. It has all kinds of mathematically provable properties of security. But exactly how secure is it, and how much does it cost us to do things in this manner? Now, in terms of security, we made an assumption that nobody lies, the system doesn't lie, and the user doesn't lie. Even under this scenario, things get very complex. But if we want to take into account that the user or the system might lie, then we have mechanisms called zero-knowledge proofs, which can verify that the entities are indeed doing what they're supposed to do without actually seeing the outcome. But all of this affects the actual efficiency of the algorithm. It becomes very expensive. And how expensive is it? Well, there are many factors here. Public key encryption, which is what we will use, is expensive. There's repeated encryption and decryption. There's repeated exchange of information. And of course, you can toss in zero-knowledge proofs if you're feeling masochistic. And that has this outcome. Now, the results that you will get are going to be identical to what you get if you were not worried about privacy at all. But in terms of computation time, here's how much time it takes to process 1 second of speech. So all of this needs encryption, and the strength of encryption depends on the number of bits you use. If you use 256-bit encryption to compute a Gaussian log likelihood for 1 second of speech, that takes 5 minutes and 47 seconds. If I use strong encryption, which is 1024 bits, that takes 3 hours and 32 minutes for 1 second of speech. Clearly, this doesn't make a lot of sense. Now, all we've done over here is to prove that it's feasible. Now, this efficiency can be improved, by having more efficient implementations, various alternative schemes like garbled circuits, better encryption methodologies, and so on. We can get maybe a factor of 10 or 20 speed up, but that's still not going to give us the factor of 1,000 or 10,000 we need for a practical application. So, but of course, this mechanism has all the nice properties. It's provably correct. It does what you expect it to do. It's just slow. But then, why do we have to even think of things along this line? The reason we run into this computational problem is that I was pretending to be a cryptologist, and I'm not. I'm an engineer. I and so were my students for the most part. So if I'm an engineer, the basic realization is that as engineers, we don't care if it's accurate to the last bit. We don't care if the information that would require, if it's possible to extract information from some encrypted data with 2 years of processing. In most practical applications, nobody is really going to waste that time on you. So, in a practical application, many of the problems that cryptologists worry about don't really apply. On the other hand, if you come up with an engineering solution, the cryptologists are not going to be very happy with you, but that's okay. So, given that, let's change the nature of the problem. All of us use computers, all of us use passwords to log in, and all of us are fairly secure with our passwords. If somebody stole your computer and got the password file from it, they still cannot find your password without actually going through the process of generating trillions of passwords and finding which one matches, because you cannot go backwards from the encrypted password to the text. There's a one-way encryption that goes in. So, and the one-way encryption that converts your text to a cryptographic hash is extremely fast to compute. So, can we actually use that? Here's how we can do this for speaker verification. We will convert the speech into a password. Now, in the case of the password, the stuff that is stored in your password file is an uninformative bit string. You cannot inspect it and know anything about what it actually says. So we would like to convert our speech recording into an uninformative bit string, much like password systems. And again, just to reiterate, we're assuming that anytime I say that the user does something, what I mean is that the user has a computation capable device which does it. For instance, it might convert my speech to an uninformative bit string. So the idea here is we would like to be able to take the enrollment recording of the user, convert it into an uninformative bit string, and then later, when you want to verify the speaker, the person is going to say something, you convert that into an uninformative bit string, you compare the two, if they match, you accept the speaker, otherwise you don't. Then the problem, once stated thus, the problem simply becomes, how do you convert a recording into an uninformative bit string? And the problem, of course, is that firstly, speech recordings can be of variable lengths. These bit strings are fixed length, so we have to worry about the length of the recording. Secondly, regardless of the kind of parameterization you use, you can use that to recover some information about the recording, so we want to erase that information as well. Let's look at these one at a time. The conventional approach, as I mentioned, you have a universal background model which represents everybody except the target speaker. You get a model for the targets which is adapted to the set of enrollment recordings by the target speaker, and then you can use a Bayesian classifier. The more common approach these days, and something that we too will use, is to adapt individual recordings of to determine the distribution of individual recordings of the user. So specifically for each recording from the user, we're going to adapt our background model to that recording to get a new Gaussian mixture, with one specific constraint that the adaptation is done by only moving the means of the Gaussians, so that the number of parameters you have to represent is limited. And then thereafter, the recording itself can be represented using what is called a supervector, which several of us here are familiar with, which is obtained by simply concatenating the means of these Gaussians. Now this has a nice effect. Your recording may be of variable length, but your supervector, the dimensionality of the supervector depends only on the number of Gaussians in your recording. So you've gone from a variable length recording to a fixed length representation of the recording, regardless of the length of the recording itself. So the verification method in this case is that the system would obtain multiple enrollment recordings from the user. It generates supervectors and generates supervectors for each enrollment recording. It also obtains a collection of imposter recordings and generates a bunch of feature vectors from these imposter recordings. And then you can train a binary classifier like a support vector machine from these collections of feature vectors, one for the target speaker, one for the set of imposters. And then when a new recording comes in, all you have to do is to sort of classify it using this SCM. So we sort of solved the problem of the variable length, but we still have other issues to consider. Supervectors are good fixed length representations, but they are informative, because if I have a supervector from you, I can use it to find stuff about you, detect your recordings in other places, and so on. So we want to convert these somehow to uninformative password string-like bit strings, and over which we can attempt to perform an exact match for authentication. So how will we do this? First, we recall that text-based password systems use cryptographic hashes. Your text password is put through something like SHA, and you get a bit string which doesn't make sense. So we're going to use a hashing function. Specifically, we'll use locality-sensitive hashing. Now, locality-sensitive hashing is a method of mapping data into bit strings or keys, which has a specific property. If I have two data instances x and y, then the hash keys of x and y are identical with a high probability if the distance between the two vectors is small. But if the distance between the two vectors is large, the probability that they'll fall into the same, because they'll be hashed to the same number, falls up very rapidly. So, and the function, of course, depends on how you define the distance. There's a formulation. I'll skip the arithmetic and sort of illustrate it pictorially. So consider this 2D example. So in a 2D example, all data lie in a 2D plane, and let's say that dot over there represents the vector that we want to hash. So we would first generate a random vector x, v, and a random shift b, which are shown by these lines here. And then the space is partitioned orthogonal to your random vector into strips. And the location of this random shift b is numbered 0. And as you go out to the right, all of them are numbered in increasing integers. As you go to the left, everything is ordered as decreasing integers. So the first component of my hash over here, hash key, is going to be the number 1, because the dot falls in the strip numbered 1. Then, for the second component of my hash key, I generate another vector and another bias, stripe the data in the same manner, and now in this case, the second component of my hash is going to be the number -2, because that is the strip in which the data falls. And so overall, the two-element hash that represents this data is going to be the sequence of numbers 1, -2. And that sequence specifically represents all data that lies in this little golden cell. So all I need to do now what has happened is that I have converted my recording into a bunch of numbers over which I can try to perform an exact match. So during enrollment, I can assume, let's say I assume one enrollment occurrence. I can convert the supervector for the enrollment to this hash key, basically find the random cell in which it resides, and then during the test, I find the random cell in which the test recording resides. And if that cell is different from the cell in which my enrollment recording lay, I reject it. If the test vector falls in the same cell as my enrollment recording, I accept the speaker. Very simple. Of course, now again, these hash keys, even if I don't give you the random vector and the bias from which I generated these cells, the hash keys give me information, because things are numbered sequentially. And so if I have two hash keys which are close to one another, I know that things are nearby. And knowing that things are nearby enables me to invert stuff and generate information if I'm sufficiently motivated. So we want to hide that. But then, of course, there's a simple answer to that. I can actually cryptographically hash even the sequence 1 - 2, so that what results looks like gobbledygook, and I can still perform exact matches. So now I've converted this to exactly the password matching problem by converting audio strings into character strings or number strings which can be used as passwords. Well, so now let's see what happens. Now in my example, I only used 2 numbers to represent my hash key. What happens is, as I increase the size of this hash key, when I add a third hash key, that cell becomes smaller still. A fourth one will reduce it further, and so on. So as I keep adding the number of complex functions, the individual projections, and increase the length of my hash key, the size of the cell becomes smaller and smaller and smaller. Now, so increasing the key length has the benefit of reducing cell size, which means that when two vectors fall within the same cell, I can be highly confident that they both came from the same speaker. But then it also makes it much more likely to miss valid instances because these vectors are random. So here, for example, I have two instances of pairs of dots. The distance between the two pairs, the pairs of dots is the same in both cases, but in one case, you would say both fell in the same cell, so you'd accept the speaker. In the other, you're going to say they fall in different cells, you'd reject him. And all of this has to do with the random orientation of the cell itself. And so we need some way of not running into this problem. So the way we'll do it is to generate multiple hash functions, which will produce multiple hash keys. Each hash key will generate a cell of a different shape and a different orientation. And so now, for my enrollment recording, I'm going to convert it to a sequence of hash keys, one using each of my hash functions. When my test recording comes in, I'm going to do the same. And then all I really have to do at this point is to count the number of matches between the two. So over here, this gives me a nice trade-off between precision and recall. As I increase the length of these hash keys, my precision goes up. As I increase the number of hash keys, I get better recall because I'm able to account for more variations. So, of course, we can't simply deal with one enrollment utterance. You need multiple enrollment utterances. And so there's an easy solution to that. I can actually have multiple, that's because people are never going to speak the same way twice. So having more enrollment utterances is always a good thing. So now I can actually convert each of my enrollment utterances into sequences of hash keys using the same hash functions. And then when my new test recording comes in, I can count the number of matches against all of my enrollment utterances. Basically count how many bars match up, and the number of bars which match up will give me some kind of a score for how well my test recording matches the enrollment. So the overall LSH-based procedure would look something like this. The user obtains a set of hash functions from the system. During enrollment, the user records a set of enrollment utterances, computes some supervectors from all of them. Then the user computes hash keys and sends them to the system, and the system stores all of these hash keys. And later, during verification, the user records a test utterance, uses the same hash keys, hash functions to compute hash keys. And now the system simply counts how many of these test hash keys match the training hash keys exactly. And you can use the score. You can compare the score against some threshold to verify the user. Now, of course, the problem here is we have only considered positive instances, and we all know that when we want to perform any kind of classification task, if all you consider are positive instances, it's not a good thing. You also want to consider negative instances of data. You want to consider, in this case, the nature of the imposter data, which is something we have ignored. And well, it's easy enough to account for those as well, in that we can collect a large number of imposter recordings and hash all of them using the same hash functions. And so now, at this point, your actual authentication scheme becomes something like this. You'd have enrollment data from the user, you'd have imposter data, all of which have been hashed in the same manner. And when a test recording comes in, you're going to count the number of matches against the enrollment data and the number of matches against the imposter data, and you can find the difference between these two. And those can be compared to a threshold to decide if the user is indeed who he or she claims to be. Now, all of this is an engineering solution. This is not the kind of solution that a cryptographer would really be happy about, but it does the job, yes.
So, you mentioned earlier, particularly with these that you gave there is a supervised backend SPN. But here you have a very simple, the world's simplest linear classifier.
Exactly. And we will get to it. So,
sorry, I have an engineering question here too. Are you saying that the imposter features have to go to the user's phone so that he can apply the same hash?
yes.
And then does he make this decision, or what does he send back?
So all the user does is to send all of these during the
all of the
enrollment
imposter's hashes and his hash
to the system during the enrollment phase. Now, the imposter recordings don't have to be They can be generated. There are mechanisms for generating these things so that you optimize your classification accuracy.
Then how does the system know that he doesn't lie about the imposter?
We are assuming that during enrollment you're honest, because at least the enrollment phase requires a motivated user. It's only later. I mean, why would you lie about yourself when you're registering with a bank?
Does the imposter data need to go to the user?
Because the user, the only person who can
He's the only
encrypt
one
the
who
data is the user. You cannot really hide the user information unless the user keeps something
No, but
on.
you could send the user the hash keys of the imposter data, right? I mean, you don't have to.
Yes, perfectly.
Yeah.
Yeah. Eventually the user performs some computation. You're
No,
right.
but the system doesn't know the same hash that the user does.
No, the system sends the user the hash key, hash functions.
And he said the system sends the user hash. I'm saying the system also sends the user the UBM.
Yeah, you can do that. That's a perfectly acceptable answer in this case. Yes. Anyway, so how fast is it? These are all extremely fast to compute, and for 200 hash keys per instance, the overhead is about 28 milliseconds on something that's the equivalent of your smartphone. So you're really not adding any overhead at all. The cost comes with performance, right? Now these numbers are not to be taken on face value. This particular experiment run on the Yoho dataset was purposely handicapped to give us really bad numbers, just so that we could magnify the errors that happen by using this mechanism. And we find that, if I used an SVM, I get a 9.1% equal error rate. If I try to use the counting-based linear classifier, I get an equal error rate of 11.86%. It's slightly worse. And everything scales down. So when I optimize all the classifiers, one becomes about 0.25%, the other becomes about 0.75%. But then what exactly are we doing over here? So if I concatenate all of my hash keys into one extended vector, then what we are really performing is a block Hamming distance computation. So this might be the bunch of hash keys I obtained from my enrollment recording. This is what I got from my test recording, and block by block I'm trying to find out if both are identical, and I'm computing a block Hamming distance over here. And the block size is the length of the hash key. So now the hash keys end up being fairly long in the mechanism in which I just discussed it, and making them longer makes things more accurate. But can we make these small, say as small as 1 bit? And the answer is no, you really cannot, because it can be proved that if I make each of these things down to 1 bit, then this becomes an instance of 1-bit compressive sensing. And well, there are algorithms to recover from 1-bit compressive sensing. So that's not an answer by itself, but there is a variant of it which does give us exactly what we want. So here is the conventional locality sensitive hashing. We numbered all our strips in increasing order. Instead of that, if I number them in a binary manner where every strip is numbered 0 and every other strip is numbered 1. Now I'm still going to get the same locality sensitive hash, except that now my outputs are all going to be binary. They're either 1 or 0 every bit. So I'm going to have, instead of having an entire hash key for every function, I'm going to get 1 bit for every function. But when I do this, so this is what we will call the Universal Quantizer. Now when I do this, it turns out has a very interesting property. It has provable, and all of which are provable. I'm not giving you the formula here. But the point is that when two data points fall really close to one another, that is, when they are within when the distance between them is less than the average size of a cell, then the block Hamming distance, which now becomes a real Hamming distance because everything is only 1 bit, is directly proportional to the actual distance between the vectors. On the other hand, when the distance between them increases beyond the width of a cell, then the Hamming distance becomes completely uninformative. So these are simulations, but you can actually write out the formula which will give you these answers. And as you can see, that if you compare the Euclidean distance with the normalized Hamming distance, you get this pretty function which is linear up to a point, and then suddenly becomes horizontal. So whether the distance is this much or this much really doesn't tell you anything about the data. Now what this means is that now I can use this to find out if two data points are close to one another, but when they're farther than a certain distance, they don't tell me anything about one another. It's a wonderful property in situations like authentication, which is where that's exactly what we really want to be able to do. We want to be able to classify with accuracy when the vectors are close to one another, when they're far away. Who cares? And we can still hide a great deal of information, although not all of it. So this gives you the true distance, but only within a cell. Now how can we use this? Let's go back and say, okay, now that I have a way of computing a real distance between two vectors, can I go back and use a more formal mechanism for classification, specifically a support vector machine in this case? Well, the problem here, of course, is that your standard RBF kernel has, satisfies Mercer's conditions. If I replace the Euclidean distance by the Hamming distance between the hash keys, this no longer satisfies Mercer's conditions. So it's not really a true kernel anymore, it's a pseudo kernel of sorts. But again, being an engineer, I'm going to pretend that it is a nice valid kernel and I'm just going to use it for classification. And so now, the verification by universal quantization mechanism is as follows. The user's smartphone computes the hashes during enrollment, retains the hashing functions as private key. Now, in this scenario, things get a little more complex because now you're down to 1 bit, revealing the hashing function to, and there's no further encryption. It's only a bit. So revealing the hashing function to the system gives away all the information. Furthermore, now you're actually not, you're not counting exact matches, you're counting distances. And so you can't let the system interpret the distances. The system only gets the hashes. And so the user sends the SBEs of enrollment and imposter data. The system trains a pseudo RDF kernel SCM classifier. During verification, the user sends SBEs of the test utterance. SBE is the secured binary embedding. And the system classifies it with a learned pseudo RDF SVM. And as it turns out, when you do this, the performance is way better than what we actually get using the simple counting-based mechanism. Again, on these, all of these results have been further improved. These are old results. But the point is that if you'll observe that with the support vector machine, with a mixture of about 128 Gaussians, we're getting on this data set, we're getting an F measure of 94.4. In fact, using the SBEs, the number we get is like 94.9, meaning it's essentially insignificantly different. You really lose nothing at all in going into this mechanism of classification. So the import of all of this is that if we decide to take into account that we are not trying to be perfect, it becomes possible to develop an authentication system with the desired traits. The system never observes the user's speech. It only obtains SBE vectors which it cannot interpret, cannot abuse the user's models because it cannot actually generate the kind of data. It will not know how to process new recordings to match it against the models. Only the user knows this. Can authenticate with high accuracy and is highly efficient. So now this is I sort of since this is work in progress, this means that my talk sort of ends abruptly, and with the final statement that this entire formalism is something that can be extended to other problems, like identifying who spoke, or detecting specific keywords, or detecting paralinguistic information, things of this kind, except of course the usage scenario would change. The system, if I'm the NSA, I generate the keys, and Verizon would have the data, and so on. But all of these can be used in a framework where a system or a user is looking for a very specific bit of information. So this can't be used for recognition, for instance. But nevertheless, in detection scenarios, it remains useful. So, and in terms of security, we are information theoretically secure to within certain bounds, but it's not entirely so. Practically, we can be certain of security simply because the kind of effort required to obtain interpretable meaning from these data is too much for the average hacker who's really interested in finding someone and not a specific someone. Anyway, so here's the conclusion. We've actually looked at, I've introduced the problems of privacy in voice, and we've looked at the specific problem of authentication. We've discussed a couple of different approaches. We've shown that cryptographic methods are theoretically feasible, but practically not. but they have all sorts of nice properties. And if you take the engineering approach of converting these problems to something that we can tackle, then we get much more practical solutions, but they are theoretically less acceptable. And this is the kind of trade-off that we're always going to face anytime we begin worrying about privacy. And that's not just something in speech, that's a universal phenomenon. Thank you.
So, okay, Andreas.
So, but once you have your voice out there, one instance of your voice, one should be able to go and do this.
If it's out there, there's nothing you can do. You lost
Exactly,
it.
so it's only if your voice has never been out there.
Yes.
Okay.
But this is for the next generation. My text is out there for my.
Right, so that was the interaction you said.
Right.
So last scheme you mentioned, right? The system would have to give the user would have to get the raw speech from the person.
So once again, in this case, for the SDEs, you don't need the raw speech. You need the equivalent of supervectors or the representation that you're using.
Yeah, okay, something that's still.
And that can be generated. There are mechanisms for a given classifier. There are algorithms enough to generate the negative instances to get the right kind of classification accuracy. So if I have a small number of negative instances, the rest can be generated. So that by itself is it's not a perfect solution, but it's not a huge problem.
Yeah, so maybe we talk a little bit about related work, because there's a whole area of privacy-preserving machine learning that must look at similar questions of secure function computation under approximations. And I just searched actually for approximate secure function computation and found some stuff by Joan Feigenbaum from 2006, which I think looks different. The privacy-preserving ML stuff may be closer.
So the privacy-preserving, the general approaches are based on protocols or based on garbled circuits. The specific distance function computation, there is a sub area where people actually try to figure out how we can compute distances between data points without giving away information. And that's basically, what we have here is along that philosophy, but the formulation is very different. The more generic mechanism uses garbled circuits, which are indeed reasonably efficient, except nobody tells you that in order to perform a single computation, the user has to send a 1 gigabyte circuit to the system. Or things like secure multi-party computation protocols, which require enormous amounts of computation and data exchange.
So I'm guessing that the computation here is smaller than the ones that the privacy-preserving ML people are doing, because they're interested in, for example, fitting a model to data from many different parties, because you're doing a smaller computation of just one threshold computation.
And there's a second factor, that here I'm not trying to be perfectly secure. The moment I give up on perfect security, I get huge gains in terms of computational efficiency. Whereas the entire area of privacy-preserving data signal processing, machine learning, and all of that.
With 0 bits, right?
Yeah. Once you become very rigid, then you're just adding layers of complexity, and all of them can be beaten by a motivated imposter. So that means I had to begin worrying about zero knowledge proofs and such like, which will always have problems. Yes.
So here, nobody's working on obviously this problem exactly, but I think a sort of collection of techniques that various people are looking at, when combined, would actually get to where you want to get potentially much more quickly. But I have no idea how it would interact necessarily with the privacy authentication. So here, replace your map, UVM, GMM with I-vector systems. Right, with I-vectors, cosine similarity becomes a natural notion of same different speaker, where you'd only need one cut per. Right, so you get around the problem of needing multiple Roman cuts, right? And then if you use cosine preserving LSH instead of E2, then you would get around all of the issues that you were doing, right? Because then you're just doing a bunch of random projections and recovering with just regular straight Hamming distance, cosine distance, and then you're done.
That would be, so firstly, the I vector versus super vector, there's really no difference. We could be using I vectors over here. The cosine.
Well, wait, no, but the difference though is the I vectors Well, no, but the I vectors get normalized, the super vectors, it's not clear that would.
It doesn't matter because if I have the I vector, I can still find out who you are from other places. So knowing the I vector gives me as much information as knowing the super vector because it can.
No, but once you normalize it, now you can compute cosine instead of.
Correct. So the difference here is the distance function that you're computing,
Right.
and you can have using a cosine preserving LSH versus a Euclidean distance preserving LSH. It's fundamentally not very different, and all the problems that we talk about will still remain in the sense that if I have cosine preserving LSH, if I have enough of these, I'm still going to be able to find out information, but I can hide it with the cryptographic hash, as I mentioned. The issue with having these things is that the accuracy depends on the size of your hashing keys, and as we saw, we get a trade-off where it doesn't really work in your benefit. And the SBs have the added benefit. It's a minor benefit in that you get a much better measure of the actual distance, whether it be the cosine distance or the Euclidean distance. But otherwise, in principle, it's the same thing. Yes.
I still struggle with the idea that an I vector tells you who I am. I mean, you're assuming that you have to hack the system to submit an I vector.
No, I'm saying that the system is evil. So the system has your I vector, then the system knows everything about you because it knows how to compute it. So the key bit over here is that the user retains something that prevents the system from computing the same kind of features that the user does.
How are you gonna compute an I vector if I don't? So if you record me and I don't give you my device, I compute the I vector, you're not gonna be able to compute an I vector like mine.
So again, if you're going to be computing, so unless you're retaining the UVM and the mechanism for computing it, right? So long as the system actually has the original universal background model, in which case having your recordings is enough for it to compute I vectors like yours, then everything is given away. If you're retaining all of the stuff with you in any case, you're still left with the issue of sending lots of data over where the distance between vectors still makes sense, which is what you're trying to hide. Thank you.
Thank you very much.